Okay, so what we're going to do is we're going to start off with a section that I find very interesting because, if you think about what we've done in this class the whole year is we've dealt with linear transformations, right, or transformations that are linear. So what you're going to notice is in this section we're going to focus on quadratic forms, and more importantly, what's going to happen is that we will discuss an important application of the spectral theorem. So what you're going to notice here is that we are going to be able to, if we're using the spectral theorem, we're somehow going to force out a symmetric matrix, and by doing so, and what's going to be interesting is we're going to deal with things that are of quadratic forms, and there's specific formats of the quadratic forms that we're going to define what a quadratic form is, where we'll be able to force out our matrix and it'll be symmetric. Then we can go after applying the spectral theorem. So let's actually do that by starting off with an example. So if I said, for instance, consider the function q of x sub 1 comma x sub 2, which equals to 8x sub 1 squared minus 4x sub 1 times x sub 2 plus 5x sub 2. And where is this going to go from? It'll be from R2 to R2. So if this is the space we're dealing with, now the question becomes determine whether q of 0 comma 0, which in this case equals to what? 0, is a global max or a minimum, okay, or neither. So what you're going to notice is going to happen here is we're dealing with a multivariable calculus type question, right? Because we're trying to find the max and minimum. Now, why is it multivariable? Because we have three variables, right? There's x sub 1, x sub 2, and q. So if you think about it, we have done this with a single variable in calculus, but now we're going to kind of take the linear algebra approach to it, which is really interesting, right? It's kind of like we're saying, okay, what we've learned in linear is we're going to kind of apply that to check to see if this is a global max min or neither, okay? So with that said, what we're going to do is we're going to use matrix techniques. So we will use matrix techniques to solve this, okay? So, and that's what we expected because obviously we're in linear algebra. So what we're going to say, okay, we're going to say, look, let's grab q and redefine it in terms of vectors. So we'll say q of x sub 1 times of the vector x sub 1, x sub 2 results in this equation, which now the question is, well, how could I break this up in forms of matrices? Well, let's take it one step at a time. So we could say, look, this is the same thing as saying what? It's the vector x sub 1, x sub 2 dotted with the vector 8x sub 1 minus 2x sub 2 to negative 2x sub 1 plus 5x sub 2. Okay, so notice this is not a matrix, this is a vector, right? So what I'm saying is we're dotting them. So notice how, and notice what happened here, the 8 and the 5 didn't really change. This negative 4, what did I do? I kind of split this in half and I gave this negative 2x sub 2 and then negative 2x sub 1 here, right? So I just split up that negative 4. But if you notice, if we dot this, I should get that back, right? Because look, I get 8x sub 1 squared minus 2x sub 1x sub 2 minus 2x sub 1x sub 2, which gives me minus 4x sub 1x sub 2 plus 5x sub 2 squared. Oh, and this should be squared, right? That's what we had originally, which, oh, I actually left that out. It should be 5x sub 2 squared, okay? So that's what we have. So that's how we break this up, right? So then we can say, look, I could take this further, right? Because look, I still don't have my matrix, right? This is a vector dotted with a vector. So we can say, look, notice we can write x sub 1, x sub 2 dotted with 8x sub 1 minus 2x sub 2 minus 2x sub 1 plus 5x sub 2. We can break this part up further. We could say, well, that's the same thing as what? X sub 1, x sub 2 dotted with, what would this be? 8, negative 2, negative 2, 5, multiplied by x sub 1, x sub 2. Now look, this is matrix multiplication. So now this broke up into what? This matrix multiplied that by that vector, which, notice what I just did here. I was able to force out a matrix, and I was able to rewrite this quadratic form, or something that's in the quadratic form, as what? X dotted with ax. That's what we did. Now what we're basically saying is this implies this q of x is equivalent to what? X dotted with ax. We came up with that equivalent expression. Or, in other words, if we want to work in terms of, we can say, and this would be x, or we would say q of x, the vector x, equals to what? X transpose ax, right? This is just basically to rewrite it in terms where we don't have the dot product. With, more importantly, what is our matrix A? A is 8, negative 2, negative 2, 5. And if you remember earlier, what did I say? We're going to apply an application of the spectral theorem. What do you notice about this matrix? It's definitely symmetric. So if it's symmetric, now I could apply the spectral theorem. So we would say that since A is symmetric, we know that there exists an orthonormal eigenbasis v sub 1, v sub 2 for matrix A. Okay, so let's go after that. Let's find our eigenbasis, and that's just literally finding our eigenvalues. So this stuff should be review for you. So it'll be determinant of 8 minus lambda minus 2, 5 minus lambda. This is my characteristic polynomial, which equals to 0. This is going to give me just 8 minus lambda, 5 times 5 minus lambda minus 4 equals to 0, which implies, I'm just going through this really quickly, 40 minus 13 lambda plus lambda squared minus 4 equals to 0, which then that simplifies to what? Lambda squared minus 13 lambda plus 36 equals to 0, which equals to lambda minus 9 times lambda minus 4 equals to 0, which gives us lambda sub 1 equals to 9, lambda sub 2 equals to 4. Okay, so now that we found this, let's go after our eigenbasis here, or let's deal with each eigenspace. So to find my eigenvectors, I will need what? This is E sub 9, which will give me what? Negative 1, negative 2, negative 2, negative 4. And we could see that this is what? 2, negative 1. So that's the span of 2, negative 1. And then E sub 4 would give me the kernel of 4, negative 2, negative 2, 1, which that's what? 1, 2. So that becomes the span of 1, 2. Okay, so then if I want to make these orthonormal, we know that they're going to be orthogonal, obviously. So to make it orthonormal, we have v sub 1 is just 1 over rat 5 to negative 1. And v sub 2 is 1 over rat 5, 1, 2. Okay, so now we're going to notice something really nice coming out of this. So remember what the question was. We're trying to figure out if q of 0, 0, which equals to 0, is a global max or a minimum. Okay, so, but let's kind of continue on with what's going on here. So what do I know here? This is my eigenbasis. So it will span all the vectors in the space that I'm dealing with, or all of R2. So going back to what we were saying is, now that I know that v sub 1 and v sub 2 is an eigenbasis, we could say then, if we let vector x equal to c1 v sub 1 plus c sub 2 v sub 2, here's what we know. If we have any vector x in R2, we could use v sub 1 and v sub 2 to span it, right, or to create it, because remember v sub 1 and v sub 2 form a basis, or to be more specific, an eigenbasis of our space. So any vector x could be written as a linear combination of v sub 1 and v sub 2, which this is stuff that we talked about in semester 1. But here's the interesting part. So we then have, what do we have here? We have q of x equals to what? We know that we said it's x dotted with ax, but now what could I do? I could express x in terms of my basis that I just came up with, or with my eigenbasis to be more specific. So what does that become? C sub 1 v sub 1 plus c sub 2 v sub 2 dotted with ax, which becomes what? C sub 1 lambda sub 1 v sub 1 plus c sub 2 lambda sub 2 v sub 2. Now let's stop here because I made a pretty big jump. See, what do we know about ax? Well, if I replace x with what? C sub 1 v sub 1 plus c sub 2 v sub 2, then what does this become? Then a times c1 v1 plus c2 v2, just to kind of make the connection. So all I'm doing is, instead of this x, I'm replacing it with the linear combination of v1 and v2. Then what would I get? I would get c sub 1 a v sub 1 plus c sub 2 a v sub 2. Hopefully you could see this. And what is it that we know? What are v sub 1 and v sub 2? Aren't they eigenvectors of matrix A? So then what do I know? A v sub 1 becomes lambda sub 1 v sub 1. That's the associated eigenvalue. And a v sub 2 becomes lambda sub 2 v sub 2, right? So that's what I did here. From here to here, I just substituted for x, and I used the idea of, or the definition of eigenvectors, right? Because if I have an eigenvector, we have an associated eigenvalue, and I wrote it this way. Now, what's nice about this is now I could perform my dot product. And if I perform my dot product, what do I get? I get lambda sub 1, c sub 1, v sub 1 dotted with v sub 1, plus c sub 1, c sub 2, lambda sub 2, v sub 1 dotted with v sub 2, plus c sub 1, c sub 2, lambda sub 1 v sub 2 dotted with v sub 1 plus c sub 2 squared lambda sub 2 v sub 2 dotted with v sub 2. Okay, now the beauty of this is what? We know that since, what do we know about v sub 1 and v sub 2? They're orthonormal. So since v sub 1 and v sub 2 are orthonormal, what do we know for a fact? V sub 1 dotted with itself will just be 1. V sub 1 and v sub 2 dotted with each other, they'll zero out because they're orthogonal, and v sub 2 dotted with v sub 2 will also be 1. So what do we get here? We're just left with what? Lambda sub 1 c sub 1 squared plus lambda sub 2 c sub 2 squared, which we found lambda sub 1 and lambda sub 2 earlier, didn't we? Which becomes what? 9 c sub 1 squared plus 4 c sub 2 squared. So this is what we're saying here. So the beauty of this is, and like we did a lot of work here, so let's not lose sight of this. But using the idea of that A was symmetric, we were able to find our eigenvectors, and we made them orthonormal. We found an orthonormal eigenbasis. And using that idea, we're able to write Q in terms of what? Just C sub 1 and C sub 2. But more importantly, we could say, look, since we found that Q of x is equal to what? 9 C sub 1 squared plus 4C sub 2 squared. And remember, these C sub 1 and C sub 2, where they come from, they're pretty much like the coordinates, right? Remember when we talked about the coordinates in first semester of our basis, right? That's what we did. But more importantly, what do we know about C sub 1 and C sub 2? Who cares what C sub 1 and C sub 2 are, right? These are any scalars, but when you square them, what do we notice? They'll always be positive. So what does this imply? Q of x is always greater than 0 as long as what? For all x that does not equal to the 0 vector. Because if the x is the 0 vector, then C sub 1 and C sub 2 will be forced to 0 out, right? Because look, if x is the 0 vector, my only solution will be the trivial solution, which would make C sub 1 and C sub 2 zeros. So this is always greater than 0, and so our focus was what? On Q of 0, 0. And what do we know here? If Q of x is always greater than 0, and Q of 0, 0 is equal to 0, this ends up being what? Is an absolute minimum, right? Because once we go past 0, 0, it'll always be greater than 0, which makes this an absolute minimum, right? So we use the idea of linear algebra to show that this is an absolute minimum, right? So pretty interesting. So now moving on to defining what a quadratic form is, right? Because we kind of worked with a quadratic form and we were able to force out these matrices, but now let's officially define what quadratic forms are. And then we'll also talk about finding the matrix, which finding the matrix of a quadratic form is not difficult. You kind of discovered that we stumbled upon that in the last example. So we would say that a function q of x sub 1, x sub 2, all the way to x sub n from Rn to R is called a quadratic form if it is a linear combination of the form x sub I, x sub j, right? Kind of like if I have x sub 1 times x sub 2 like we had in the first example, and where I and j also may be equal, right? So where I and j may be equal. Okay, so basically what are we saying? This is a quadratic form if we have a linear combination of what? X sub I, x sub j. So it could be any combination, right? X sub I and x sub j could be equal. Kind of like if you look at the first example, we had what? We had x sub 1 and x sub 2. Now, we don't have to have, these subscripts could be anything, but it's just they have to be in pairs, right? So it's just have to be x sub I, x sub j, right? We can't have a third one, right? Because then it won't be quadratic. So we would then say a quadratic form can be written as a q of x equals to x dotted with ax, or equivalently x transpose multiplied by ax. Okay, so this would be what? For a unique symmetric n by n matrix A, called the matrix of Q. Okay, so here's the interesting part. See, now we're dealing with quadratic forms where we know that they're not linear, but we're able to force out a matrix in which that matrix A ends up being symmetric, which allows us to use the spectral theorem, so then we can kind of find a basis, an eigenbasis, and so on, which we're then able to work with quadratic form, even though we literally like to work with linear equations, right? But this is one way of kind of dealing with certain instances where we don't have a linear transformations, but we could still force out a matrix out of it where we can work with it, right? So a lot of interesting things going on here. Now, this next example, I'm going to kind of show you guys a nice convenient way of finding this matrix A, right? As long as we know we have something of a quadratic form, I'll show you a nice convenient way of finding this matrix A. So example 2 is going to do just that. So we're going to say, look, consider the quadratic form Q of x sub 1, x sub 2, x sub 3. And remember, it's okay if I have x sub 1, x sub 2, x sub 3, except when we're dealing with quadratic forms, we can only multiply 2 of them at a time together, right? That's by definition what a quadratic is. So it'll be 9x sub 1 squared. And see, this is what x sub 1 times x sub 1 plus 7x sub 2 squared plus 3x sub 3 squared minus 2x sub 1 x sub 2 plus 4x sub 1 x sub 3 minus 8 x sub 2 x sub 3. So then we're going to say find the matrix of Q. Okay, so now to find the matrix of this, that's actually very straightforward, right? Because here's how I think of this. I think of the indexing. So this is going to be a 3 by 3. How come? Because we have 3 variables here. So here's what we know. The x sub 1 squared, x sub 2 squared, x sub 3 squared, those are going to be on my main diagonal. Now, how come? The way I think of it is this. See, this is x sub 1 times x sub 1. This is x sub 2 times x sub 2. So this is saying what? X sub 1 times x sub 1, that's row 1, column 1, right? So row 1, column 1 is this first entry, and the 9 is going to go there. This is what? Row 2, column 2, which is 7, so that'll be 7. This is what? Row 3, column 3, which is 3. Now, the other one, see, this says, now here's what we have to be careful about. These guys, using the same idea, would be what? Row 1, column 2 would be the negative 2, except what do I need to do? I need to cut this in half. How come? Because this is a symmetric matrix. So if this is row 1, column 2, this is negative 2. In row 1, column 2, I'm going to put a negative 1 because I'm cutting that in half. But also, since it's symmetric, row 2, column 1 will also have the other negative 1. So look, this negative 2 becomes what? Negative 1, which if I add them, notice how I get the negative 2. Now, as far as the placement goes, how do I know where to place them? These indices tell me that. This negative 2 is going to be cut in half, which will be, so we divide by 2, and that becomes what? Negative 1. So in row 1, column 2, I'll have a negative 1, and in row 2, column 1, I'll have a negative 1. So then, how about this 4? That 4 is going to be cut in 2. It'll be a 2. In row 1, column 3, I'll put a 2. And in row 3, column 1, I'll put a 2. And then lastly, what do I have? Row 2, column 3, I'll put a, since this is negative 8, if I cut it in half, I'll put a negative 4 there. And then in row 3, column 2, I'll put a negative 4 there. And notice how I constructed my matrix. And sure enough, this matrix is literally what? It is symmetric, right? If I take its transpose, I'll get the same thing out of it. So this is a nice, quick way of finding the matrix A of any quadratic form, right? So hopefully you're okay with this. If there's any questions you have on it, don't hesitate to reach out to me. Now, the next few definitions, I'm just going to go through these pretty quickly, and we're going to have a couple of theorems. We're not going to prove them, but we may talk about them at some point. So the next definition is 8.2.2, which has to do with definiteness and quadratic form. So we're going to see, hey, is this positive, definite, and so on when we're dealing with quadratic forms. So we're going to say, consider a quadratic form q of x equals to x dotted with ax, where a is symmetric, so then we're going to say, well, symmetric n by n matrix. Let's be more specific here, right? Because what type of a matrix is it? It has to be n by n. It has to be square, right? So we say that A is positive definite if q of x is positive for all non-zero x in Rn, and we call A positive semi-definite if q of x is greater than or equal to 0 for all x in Rn. Okay, so if you think about it, example 1 was what? It was definitely all the q's were positive for all non-zero x, which made it positive definite. Okay, so what we would say is, well, negative definite and semi-definite is defined similarly. All right, so same idea, I just don't want to rewrite the whole thing, okay? So, and then what happens if A is indefinite? So A is indefinite if Q takes on both positive and negative. If Q takes positive and negative. Values. Okay, so with that said, let's look at our third example. So the question or the statement is, if A is skew symmetric. Now, if you remember, what did it mean if it was skew symmetric? That just means A transpose is equal to negative A, right? So if something is skew symmetric, when you take its transpose, you get its opposite, right? We defined this earlier on in the year, so just in case if you'd forgotten, that's what we mean. The question then is, what can you say about the definiteness of A squared? So then the question is, I guess, the first question is A squared symmetric? Right? Because if it is symmetric, then we can use the ideas of quadratic forms and so on, or we could use the ideas that we've talked about earlier on, and so we can go with that. So what is it that we want to show? We want to show if it's symmetric, then we need to show that. So we want to show A squared transpose is the same thing as A squared. So if we do that, let's kind of start off with A squared transpose, which that we know is the same thing as what A transpose squared, right? We can do that. And what is it that we know? A transpose is going to be negative A squared. And what is it that we know? Negative A squared will just, negative A squared will just literally be A squared. So sure enough, it is symmetric. And if it's symmetric, now we can say, well, I have a symmetric n by n matrix. So now we can say, now consider the following. Our quadratic Q of x, which is x transpose a squared x, which gives us what? X transpose a ax, right? I just expanded this out. And then what is it that we know? We can say that this is the same thing as negative x transpose ax. Now, why did I do that? Because I'm trying to get these guys to match up. And what do we know? Since it's skew symmetric, a transpose of if I take the transpose of this, I get the opposite of it, right? Because it's skew symmetric. And then this becomes what? Negative ax transpose. And I use the idea of the transpose, right? So remember we talked about this earlier. Ax transpose becomes x transpose A transpose. So I went the other way, times Ax, which gives me what? Negative Ax dotted with Ax. If you remember, this is Ax is in fact a vector. So instead of saying this, the transpose of this vector, instead of using matrix multiplication, I could write it as a dot product. That's what I did. And what do I know? Ax dotted with Ax, we know that's the same thing as what? The magnitude of Ax squared, which gives me what? Negative magnitude of Ax squared. Which, what do I know about this? The magnitude is always what? A positive number or 0, right? So with a negative in front of it, what does that mean? This is less than or equal to 0 for all x, which what does that imply? And it's actually really neat how it worked out the way it did, right? So remember, symmetry was important for me to be able to write it in quadratic form, right? If it wasn't symmetric, then I wouldn't be able to write in quadratic form. So I was able to grab that matrix and say, okay, I know I could rewrite this in quadratic form. And what does this imply here? A squared is negative semi-definite. Okay, so with that said, now let's go on to the next two theorems, which I'm not going to give you the proofs to these next two theorems, but you may need to work on them at some point in this course. So theorem 8.2.3 has to do with eigenvalues and definiteness, which this one says a symmetric matrix A is positive definite if and only if all of its eigenvalues are positive. Okay, and then we would say the matrix A is positive semi-definite if and only if all of its eigenvalues are positive or 0. Okay, so this actually some interesting. This is an interesting theorem. So think through this. See if you could kind of work through with this and get it to kind of to work out. Okay, so and remember it's an if and only if, right? So see if you could kind of get the ideas of quadratic forms and so on, and show that it's positive definite or positive semi-definite and so on. Okay, so and the last theorem that we're going to talk about is theorem 8.2.4, which has to do with diagonalizing a quadratic form. Okay, so we would say consider a quadratic form q of x equals to x dotted with ax, where A is a symmetric n by n matrix. Okay, so then we would say let script B be an orthonormal eigenbasis for A. And if you remember, we did that in example 1, right? We came up with our orthonormal eigenbasis with associated eigenvalues. So if you look at kind of like the setup, that's what we did in example 1, right? We came up with an orthonormal eigenbasis for A, and then we had our associated eigenvalues, lambda sub 1 all the way to lambda sub m. Okay, so then we would say then q of x could be described as lambda sub 1, c sub 1, v sub 1. Oops, sorry, it should be lambda sub 1, c sub 1 squared. We lose the v sub 1 if you remember, because it was orthonormal, right? If you remember, that's what happened. And then plus lambda sub 2, c sub 2 squared plus lambda sub n, c sub n squared. And then we would say that where c sub I are the coordinates of x with respect to our eigenbasis. So if you think about it, we did this in example 1, except it was when we had two vectors, two eigenvectors. But if we were to grab the idea of example 1 and extend it out to, hey, if I have m eigenvalues, then I should pretty much be able to force out the same idea, and this should be a c sub m. Sorry. So just to keep this in mind, we can do this same thing, or we can prove this by using the idea of example 1 and extending it out to, hey, if I have m eigenvalues, how would that work out? Okay, so and we remember the eigenvectors here have disappeared, because when I took the dot product, what happens when you dot a eigenvector, if it's orthonormal, if you dot it by itself, you get 1, and then if you dot the other eigenvectors to one another, they zero each other out. Okay, so that's kind of what's going on here. So this is where I want to stop with section 2. There's plenty of material here. Now, if you have any questions, don't hesitate to reach out to me, and I'll be more than happy to answer it. But this basically wraps up section 2.